All right, good afternoon, everybody. Just taking control of the slides here. Thank you for joining us again for day two of our integrated planning workshop, sponsored by Breakthrough Energy. So thank you to those folks. Yesterday, day one, we spoke about traditions for resource planning and stability, special topic on the Iberian blackout, and some introduction to fundamentals for power systems dynamics, voltage stability, and frequency stability, with some Q&A at the end there. So after yesterday's session, we will be posting the recording as well as those slides, and a small sheet of any of the questions that y'all put into the Slido that we did not get to during the Q&A discussion yesterday. Those will all come sometime soon. So similar to yesterday, we're going to go through some interesting topics here and some concluding remarks and question and answer again at the end there. Similar to yesterday as well, any questions we don't get to, we'll pass those out with today's recording and today's slides. For those who did not see the first slide as you joined here, it's slido.com and the password is ESIG16. So ESIG, and today is the 16th. And please put any questions in there as I go through, or as Wallace and Carlo go through today, and we'll handle those in the Q&A. I do have it open on the side here, so for my presentation, if a question comes in that's I can handle while going, I'll do that as well. So with all that, and without eating up any more of our time, let's just get started, and I'll jump into the first topic of today, which is planning and modeling of IBR dominant systems, and what is different. Oops, that's a thanks. I don't want to see that. Lacey, could you? Oh, thank you. You got it. Perfect. You read my mind. Thank you so much. We're using a very awesome WebEx feature here today to control without having that happen. But all right. So what we'll handle today, or I'll cover today for the next 44 minutes, if we're lucky, is planning and modeling IBR dominant systems. My name is Alex Shattuck, and I'm the Director of Grid Transformation at ESIG, the Energy Systems Integration Group. This is a very hot topic. Modeling is one of those things that has been in my mind for, I don't know, 6 to 8 years now, very strongly. And it's one of those things that just recently the industry as a whole has really started talking about and discussing. And a lot of the things that I've been personally pushing for or advocating for best practices are finally seeing some public discussion, and even some public regulatory enhancements. So for this presentation today, I'll get into that, but I think to understand why modeling is important, and understand where we need to go, and where we need to go to fix these gaps, is very important to start with the history, right? The past. We can learn a lot from the past. We can hopefully apply those lessons that we've learned to the future. So just quite frankly and very plainly put here, and very bluntly, the current paradigm isn't working. What we as an industry are doing right now with respect to reliability of the power system is not working. How do you improve the reliability of a system or of the processes that drive that reliability? Well, you need to understand the results and the current operational results of what's happening right now under the current paradigm of FERC compliance or FERC regulation, and local requirements and performance requirements and interconnection process requirements. So for those of you who have seen me present or NERC presentations, this is a very often right in front and center. But since 2016, there's been a little over 15,000 megawatts. And this is an older graphic, so there's a few more events here, but we'll call it 15,000 megawatts of inverter-based resource events that were classified for major disturbance. So what this means is these are just the events that qualified for the mandatory reporting criteria from NERC. So there's a couple of classes there, a certain threshold there, which I think is 1,600 megawatts or so, of some discretion there for other factors. Those get a mandatory report. So these are just those that had mandatory reports from the NERC side. So what that means is that there are additional events that were not captured in this total of 15,000 megawatts. So to be very clear, also, if you look to the right here, these are all either solar photovoltaic or battery energy storage facilities, except for the Panhandle Wind, number 7 there. And the reason for that is, by and large, and this is kind of a general statement, if a solar PV plant or a battery energy storage plant trips, it trips this in its entirety, right? So if I have a 100 megawatt solar PV plant, if something trips, usually that whole 100 megawatts comes off, which means that you very easily or more easily get to that threshold that means you have to mandatorily report and analyze that event. What you miss there, and what kind of is a little insidious in a way, is for wind, specifically wind. So, um, at the simplest, both wind or Type 3 and Type 4 wind, which are more modern wind, they, just like BESS and just like solar PV, they interact with the power system with power electronics. Um, those power electronics are kind of susceptible to a number of tripping kind of procedures or events, voltage, frequency, DC voltage, controller interactions, different thresholds, capabilities, and things like that, uh, where even just a simple parameter change or a mistake or a failure to update can lead to kind of entire plant tripping or individual unit tripping. So wind and solar are both susceptible to very, very similar causes of reductions, what I'll call them here. So the difference is a wind farm has a much larger collector system, which is the cables that connect those inverters to the actual substation that interfaces with the power system, which means you get a lot more variation between what each individual wind turbine is seeing at its own terminal as an event happens at the power system level, or and it propagates through the plant. So what happens very often in wind facilities is you may see something called partial trip, which is maybe half of the wind turbines trip offline, but the rest stay online, which means that you may have an event where 10 PV plants trip offline, and they're 100 each. That's 1,000 megawatts tripped offline. You may have a very similar event where 10 wind farms of 100 megawatts each partial trip, and that's about half the size. So just for example speaking. So um, all of that is to say that 15,000 megawatts is a lot. This is just solar PV. Wind is not reported here. There has been some research done and some studies done to show that they're both susceptible to the same. Um, and partial tripping is a big problem too for wind. So what's that? All I'm saying is that this 15,000 megawatts, while very striking, is really not even all of the major events here. So the other key thing before I move on here for these major events is that the reason why these are major events is because they weren't expected. And the reason why they weren't expected is because the studies that were done, planning studies, interconnection studies, well, planning studies specifically, for these contingencies, they did not show these inverter-based resource performance issues in those studies. The other main thing to note about these major reports is that these are all normally cleared, normal contingency events, things that are in the planning contingency decks. Contingency decks are just the events that you would run as a planner. So what that means is there's 15,000 plus all the considerations for wind, megawatts of inverter-based resources that are tripping offline when all of the studies say they shouldn't. And that's not great. It's not a great representation of the current paradigm. So additionally, when we've dug into these, for reference, I used to work at NERC and did some of these investigations. But when we looked into these facilities, so when an event happens, like Odessa, for example, we contact, the resource owners. We get their models, we get their information, and we try to see if those facilities, those models of those facilities, will match the performance that was recorded during the real event. So I guess I'm going to say positive, but it's not super positive. The positive thing about a major event is that there's some leverage there to go pull data from each of these plants or measurement devices around the grid, and you can compare real world with what was modeled. And during those exercises, in all 10 of these events, in all of the affected facilities, maybe 10 plus per, So over 100 plants, IBR plants, not a single one of them, of those plants, when we studied their models, not one of them had a model that matched how it actually performed, which is, again, a very clear indication that the paradigm isn't working. If we're not seeing any matching, and I'm going to repeat that a bunch of times throughout, um, the studies, the models, the inputs, there's a disconnect somewhere, there's a gap somewhere, um, and that's leading to these major disturbances and unexpected events. And honestly, it kind of diminishes the purpose of doing those studies. If we know that the results of these studies are inaccurate, it's hard to justify keep doing those studies if we know that the results are right. So we really need to reassess and realign modeling practices, requirements, best practices, and things like that, to ensure that the inputs are better, which would hopefully kind of follow through, and the outputs that we see will be better, which means hopefully that study results will show these major events before they happen, and then we can mitigate them and hopefully not have them happen again. Um, why or what's driving some of this? And I think Nick mentioned this or touched at it a little bit yesterday, but um, the motivations of IBR interconnection aren't any more aligned with grid reliability. And it looks like the eyes got vanished. It's very weird. But they're not aligned with grid reliability. Nick mentioned it yesterday, but I'll briefly kind of rehash it today. We're moving on from a paradigm where it's a vertically integrated utility, or a large natural gas turbine developer, engineering company, engineering values, a paradigm where it's kind of trust but verify, or you can kind of trust that those engineering minded folks were going to go above and beyond the technical minimum floor for requirements, just because of the nature of the technology being very mature, engineering companies doing the work, and all those principles kind of aligned that way. So we're moving on from that. And part of that alignment or realignment is kind of the double-edged sword of a lot of those tax credits that we saw um, from the Obama administration a few years ago. Those were great to get inverter-based resources, renewables, cost-effective, and get integrated into the grid. Um, what that also means is that there's a lot of money to be made by non-engineering companies. So what we've seen is, a lot of investor-owned, stakeholder-driven companies doing massive interconnections of IBRs in the US to kind of make use of those tax credits and kind of make money by selling power. And that motivation, the motivation to interconnect very quickly, as fast as possible, and make money, and the motivations for keeping the grid very reliable and doing above and beyond the extra to ensure that reliability, you can see where the disconnects happen. There are many decision points throughout the interconnection process and planning processes where you may have to decide, you editorial, whether I want to perform extra engineering work or move the project along and get to interconnection and selling power quicker. And I think we can all have experienced, which decision takes precedence there. And kind of additionally to that, and kind of adding confusion to this, is that the current regulatory structure in North America specifically, the way that FERC speaks to NERC, NERC speaks to individual entities, they all kind of point to each other, that promotes and enables disparate, misaligned, and sometimes very confusing requirements. These requirements are confusing even for detailed engineering firms who do this all of the time. So that's doubly confusing for those who are using, those kind of investor-owned, less technical developers who may not even have the expertise. So the confusing requirements are even more confusing, and it kind of really harms the quality of the inputs of the interconnection process. Finally, on this slide here is a lot of the regulatory enhancements that need to happen. They're driven by, or they're made by stakeholder-driven processes. At the moment, those stakeholder-driven processes are failing to produce sufficient technical minimum requirements for a number of reasons, ranging from kind of a lack of understanding of the nuance of inverter-based resources and what needs to happen to ensure reliability through the study process. There are utilities there are other stakeholders who may not know how to do all those studies that are necessary, and they may vote against them. There are developers who are making money not doing them right now and may vote against more enhancements. Um, and the stakeholder processes themselves, when trying to incorporate what FERC is saying, there are sometimes misalignments between the FERC directives and technical fact, and best practice, and those mitigations are very difficult as well. So all of that is to say that what's happening right now is resulting in, countless, not countless, but 10, and accelerating. If you look at the right major events, none of these events show that we captured it in the study world, and then there's motivations kind of lying behind those things. So to show kind of more of this fact that the paradigm isn't working, NERC released 3 alerts on inverter-based resources, one level 2 alert for performance, another level 2 alert for modeling considerations, and a third alert, which is a level 3 alert, which kind of combines the two and gives essential actions. But the findings from that first report show, and this is a quote that I wrote for that report, which is the voluntary recommendations, right? Those set forth in NERC guidelines, other publications, the NERC IRPS, all those white papers, they're not being implemented. Just straight out, right? How do you fix that? Well, we need to take the presentation like today, understand why modeling is difficult, understand what needs to happen, and use that knowledge to enhance the regulatory requirements so that they're mandatory. In the current world and the current paradigm of the North American power system, if it's not mandatory, it's probably not going to happen. And the evidence of that alert, the actual need of making an alert like that, and the evidence in the self-reported data show that if it's not mandatory, it's not going to happen. If it's voluntary and it costs a little bit of extra money, it's not going to happen. So planning a reliable power system in general depends on accurate modeling of the system and everything connected to it. What I'm going to focus on here today is modeling IBR performance, so the actual inverter-based resource, the wind plant, the solar plant, the battery energy storage plant, modeling themselves and their performance, themselves and their components like collector systems, transformers, cables, things like that, substation equipment, and anything that may take that facility offline. So when we talk about major events, NERC has kind of categorize them into separate kind of causes of reduction, I'll say. And this below is from the 2022 Odessa disturbance report. And this just goes to show what can be actually modeled in different simulation domains. So there's 2 different simulation domains. One is the positive sequence or phasor domain simulation domain. And that's something like PTI, PSSE, Power Factory is both, but PSLF, which is GE's product, things like that. And then EMT, which is electromagnetic transient, a little bit more detailed, a lot more computer intensive modeling. And you can see on the left-hand column here is there's a lot of no's in the positive sequence phasor domain column for these causes of reduction that NERC has observed, which means that the current paradigm of doing basically only positive sequence phasor domain, and I'm saying basically only from a regulatory standpoint, you're not going to capture, about half or more than half of those things that we have, or NERC has called out as real world issues and causes of reduction. If we keep to the current paradigm of focusing mainly on phasor domain positive sequence simulations, we're missing it just by virtue of not using the correct simulation domain. If you kind of shift your mind a little bit and move on to EMT, electromagnetic transient, which again is kind of the advanced version of study work, you got a lot more yeses here. Pretty much all yeses for capturing those causes of reduction. The only one that is a no for the EMT is feeder under frequency. And the reason for that is that there just aren't, in the phasor domain or the EMT domain, those types of models available from the manufacturers of those feeder type relays. There's lots of reasons for that. The main reason is that it's just really hard to get those to work right. And it's just very hard to model them in that space. And the major manufacturers, which account for most all of those relays and protection functions, they're not making those models. So they're just not available. And that's why there's a no there. So If we keep to the current paradigm and only do phasor domain, we're going to miss a lot of things. If we move on to EMT only, we will catch a lot of things, but that's also significant other considerations for EMT only, like knowledge of the stakeholders, computers, and simulation times. So what that means is we need some sort of combination of both, which I'll get into a little bit later how that could work. Is we need kind of a combination of both phasor domain and EMT simulations. Doing maybe part of the interconnection process in the easier, faster phasor domain, doing more detailed stuff in the EMT domain, and knowing when and where to use those tools and how to use them is super important for kind of a holistic, integrated modeling scheme there. So what's so different? So I kind of spent a little bit of time there talking about what's bad right now, what's out there, and let's just talk about why that is and what's different. So we're going to start with the technologies themselves, and I'm going to lump everything renewable into IBR on the left, and I'm going to lump every synchronous machine into the same category on the right. I apologize for this super oversimplification, but they're important. So we're going to start with just technology. Big difference, especially related to modeling, is the first one here, which is when I have a synchronous machine, it's a large rotating mass of metal. It's spinning. That spinning is really driven. The performance of the machine is driven by that giant metal thing spinning. When you model that, you have the size and the weight and the speed at which it's spinning, and all of those are very physics-based performance, which means modeling that physics-based performance is relatively easier. Right? Physics has been around for a while. Obviously, those equations for spinning mass and synchronous machines are much more simple, predictable. You know about what's going to happen. You can model that physical relationship much easier, and you can model those from kind of recording physical components once it's built. The flip side for that driven by physical machine properties is that it doesn't really happen in the inverter-based resource world, right? There are some physical machine properties that do cause performance differences, capabilities of things of active power, reactive power, capabilities of voltage support and ride through, and maybe type 3 wind or type 4 wind that have an actual spinning mass. It could affect the performance. But by and large, especially for solar photovoltaic and battery energy storage, the performance is software based, right? So it's just code. So when you talk about kind of mapping that from synchronous machine physical properties, modeling the physical equations, to modeling things that are software written by software people, we're moving on from kind of mechanical electrical engineering mindset to software development and software code, and that type of change management process. So that's a huge difference in mindset and thinking, where a synchronous machine is pretty predictable, and it's going to probably do the same thing for the life of the facility. A software-driven power electronics interface device, a firmware update by accident changes that performance. Could be massively, one parameter could change performance massively, and tracking those things is very important. Another big technology difference is synchronous machines provide a lot of inertia, high fault current. IBRs, on the other hand, have little to no inertia, generally not very much at all. Very low fault current, which has repercussions for planning system protection and things like that. IBRs are more sensitive a little bit to kind of disturbances on the power system. They may read in a signal and their software code tells them to do something very extreme. They can do IBRs can do very fast, very flexible ramping, very fast frequency control, very fast reactive power control, on the order of half a second. Shorter than that, very fast ramps. You could get a massive swings in the full output of an IBR plant in a second or fewer or less. Whereas the inherent inertial response of synchronous machines, they're slow ramping. That type of thing is much less severe. It can be much less severe and much more predictable. So those types of things are very, very different. Dispatchable and fully dispatchable based on just what's available. Synchronous machines, if we assume there's always gas or fuel, you can basically tell them to do whatever they want. You can dispatch them up or down. IBRs, on the other hand, you're kind of limited by what's there, right? Is the battery charged? Is the sun shining? Is the wind blowing? And that's what you get out of it, or as a maximum. Both can provide essential reliability services. However, both can do them differently, and the reliability services necessary will change based on the penetration of each of those resources. So breaking it down, I guess I kind of covered it here, but breaking it down very specifically, the software-based inverter-based resources are significantly more complex than a synchronous machines model. We got to look at it from a software development lens. Every line of code is very important. Every single parameter is very important. And when I say every single parameter, I'm not talking about just the kind of typical tuning parameters you might see if I'm an end user of a model, which is, you know, voltage deadbands, frequency deadbands, some gains, things like that, that you interface with your utility and they tell you how to set it for performance. Each one of those maybe other kind of hidden or less used thousands of parameters. Any one of those parameters, a wrong value could have massive effects on the performance, which is different than the relatively fewer synchronous machine parameters, which have a much more clear link to the real world in kind of measuring and doing that type of thing, and measuring, putting it back into the model. The other key huge difference is that synchronous generation technology is significantly more mature than inverter-based resource technology. What that means is the synchronous machines have had about 100 years or so to standardize their technology. And that technology is a little bit easier to standardize since it's large spinning machines. That immaturity in the inverter-based resource realm, and the software-based nature, and the kind of North American propensity to patent lots of things, really makes it difficult to standardize. Which means that if I have 3 wind farms from 3 different manufacturers, those could have significantly different, or they probably will have significantly different implementations for even simple things like voltage control. So like a manufacturer A develops a voltage control scheme first, and they patent it. Manufacturer B has to have a different implementation, which means that those 2 software codes are going to be very different. And how do you standardize 2 different things when one's patented and the other one's also patented? It adds a lot of complexity, and it makes standardization very hard, which means, and I'll talk about this later, but using standard library models is very difficult to show accurate representations of inverter-based resources when compared to synchronous machines. On the kind of system-wide perspective, the lack of inertia, as IBRs are increasing penetration, inertia is lessening. I'm using inertia and weakening in quotes. Inertia and weakening aren't the best terms. There are more specific terms, but I'm using those today. The benefit of the IBR, even though kind of it's a weakness of them, is to have the little inertia and very little fault current, is that a lot of those inverter-based resources can utilize advanced grid services that they have in their own controls, their own software schemes, to operate in these kind of new conditions. The only way to do that, however, again, is to use those manufacturer-specific models that have those actual controls in there and the code in there. Because, like I mentioned just previously, one service in one manufacturer, one service in another may be vastly different, even if they do about the same thing. So making sure that you can actually model those things in their nuances is very important. A lot of the design, specifically protection, line ratings, transmission system relays, are all made under the assumption, or mostly planned and operated under the assumption of significant fault current and significant inertia. So with that changes to protection design and operation, changes to automatic voltage and frequency control, both the dead bands where you operate within, your gains and how to get there, controller interactions, those all need to be considered in this new paradigm of high penetration of inverter-based resource. Emergency power system operations, things like under frequency load shedding specifically, and linking that specifically to inertia. If there's less inertia, frequency will move much more rapidly and more widely. And I think, and Sam mentioned that a little bit yesterday in his fundamentals piece. And if those are changing, if the deviation of frequency is larger, we need to reassess emergency operations like load shedding and things like that. And the standardization of performance and requirements is also necessary. So notice I'm not saying standardization of implementation or standardization of features or capabilities. I'm saying standardization of performance and performance requirements. So that kind of gets away from the you must do something this way, and just say you give me, you IBR give me the grid, a standardized set of performance. I don't care how you do it, just give it to me. And that helps with the software based and the kind of patent issue there. But it's very important to move to that standardization kind of context of performance at a plant level when talking about high penetrations of inverter-based resource. Okay, lastly, so we did technology, we did the system, and now the stakeholders. And this is a little more detailed about of what we talked about a little yesterday with Nick, is for the synchronous paradigm, you often have engineering staff, engineering firms, reliability standards at the minimum. Getting detailed plant information is pretty relatively easy. If it's a natural gas turbine, I can go to the turbine itself. I can measure its X double prime D or other physical components. I can maybe even go read them off the nameplate. Super easy, and put them right into a model. There's also a lot fewer pieces of equipment, perhaps, at that synchronous machine. Detailed information is available much sooner in the process for a synchronous machine. I know that I'm building an X manufacturer, X size turbine. I know it's going to spin about the same, and I can kind of estimate those parameters and put it into a model, and that model might be pretty darn close, even way at the beginning of that process. The difference between studied and real are typically smaller, right? Again, just like I just mentioned, if I know I'm building a certain size turbine, if I go and take that turbine from the factory and it's very slightly different, I change a physical parameter, and probably the performance is pretty darn close. And that follows again for as-built information and modeling, and there's a lot more operational awareness, and I'll cover that one at the very end. But we go look at the IBR paradigm. A lot of them, like I mentioned before, non-engineering firms, not engineering staff. Reliability standards are the maximum most of the time. My experience has been that instead of kind of enhancing a study process or practice, a lot of times folks will spend their time and resources arguing that the standards are too much and argue down, which is probably not the best way to ensure reliability. Detailed plant information is much more difficult. The interconnection process for inverter-based resources happens relatively quickly, sometimes before even the developer has picked a manufacturer, just by virtue of the process. That coupled with the fact that one specific inverter-based resource might have one platform but 10 different software versions. You don't know which one you want, that type of thing. It might change, it might be firmware releases or bug fixes. Getting plant information about the detailed plant information for modeling is much more difficult. And because of that, and because of the software-based nature, mistakes lead to bigger discrepancies. And then also finding as-built information can be very difficult, just for all the same reasons above. And lastly, on the operational awareness piece, just a small example from my experience. This was actually the Odessa 2022 event, and there was one synchronous machine that was involved in that event. When we contacted all of the affected facilities for that event, when we contacted a lot of the IBRs, many of them said, "Oh, I didn't even know I was involved in a disturbance. We're happy to help," and we kind of started the process from there. That synchronous machine, when we contacted that synchronous machine, they essentially said, "Yep, we saw it. That was a month ago or 2 months ago. We've already fixed it. Here's our change plan. Here's our evidence that we fixed it, and it's not going to happen again." So that difference in situational awareness is very, very stark in the processes and stakeholders here. So that's the two paradigms. That's what's different between the two technologies and the stakeholders and for the system. And now we're just going to quickly go through why is modeling hard in general. And a lot of this is a little bit similar to what we said before, or what I mentioned before, but the main considerations are maturity of the technology and construction, technology performance, and the modeling parameters. So I won't spend too much time on this slide, but it's a little bit better organized version of what I rambled on a little bit earlier. But just to hit the high levels, parameters and controls are standardized, much more standardized, and relatively simple plant construction and controller construction. For synchronous machines, much more complex on the inverter-based resource side. You can standardize performance, but it's hard to standardize parameters and controls. Again, like I mentioned before. Technology performance, largely dictated by physical mass, small variations in performance when variations between different control parameters, much larger variations in performance, and then also rarely dictated by spinning mass, except for a couple winds, and much more software-based, software-affected, and software development speed as far as changing how those parameters work in codes and bug fixes and things like that. The big thing here is at the very bottom here, and this is very important when we talk about actually doing a system study or doing an interconnection study. Those studies are much more useful if I can do something in the study world and make it a change to that model or that plant in the study world and put it into the real world, right? If I can't, why am I doing this study? And how do I make sure that I can actually fix something in the study world and put it into practice? So for synchronous machines, there's a lot better mapping. Many of them are one-to-one, right? I can read, the model has input for physical characteristics. Since everything's so standardized, a lot of manufacturers use the same parameter names and units and things like that, which means you can go back and forth between the real world and study world much easier. There's also fewer things to worry about, fewer parameters in the synchronous machine world. On the flip side, very few models have one-to-one mapping. Standardized models, standard library models, more generic models, they have no mapping with the equipment, or no one-to-one mapping. There may be equations or transpositions, things like that. There's also thousands of parameters. Not all of them were exposed to the end user. Some of them are legitimate just for the manufacturer only, specific to that equipment. It shouldn't be touched. But there are thousands of parameters, and that lack of mapping really reduces the quality of the inputs and reduces the ability to actually tune something for an IBR and actually put it into the system. Right? If I fix a controller interaction, I might not be able to put that same tuning into the system and fix the real controller interaction. So that's in general why it's difficult to model inverter-based resources, everything on the right. But just to be very specific, North America has an interesting problem, and we're about the only ones to have this problem at the moment. But when we talk about modeling, and we talked about kind of synchronous and IBR modeling, but now we're moving on to just IBR modeling here. But when we're in the world of IBR modeling, there are kind of three major categories, really two major categories. I'll lump them both together. But there's the generic and standard library. Those are the ones that are publicly available. They were made from academic groups who took inputs and performance data from many different manufacturers and kind of put together a standard model that's publicly available and open source with clear documentation that should be used or can kind of replicate a specific piece of technology, right? Type of technology, right? So essentially, imagine you test 10 cars, you take all of the car's performance, you average it all together, and you have one model that could possibly represent each of those 10 cars relatively close for some specific application. So the flip side of that is equipment-specific models. That's from the manufacturer themselves, that has the real model code, has the actual information from the manufacturer, very detailed, very technically thorough. The problem with that is they're not publicly available often because of intellectual property, but there are significant accuracy and usability improvements there. So what's happening in the US is that interconnection and planning requirements often don't allow or disincentivize the use of these models, the equipment-specific models. Vendor-specific models aren't allowed to be submitted or are disincentivized with extra scrutiny or even extra costs in some interconnections, or most interconnections, costs in some interconnections. So, I've experienced in my own work, uh, if you ask an interconnection, hey, can I use a vendor-specific model? The manufacturer says they don't support the generic model, and they'd say no, or they'd say sure, but it costs $20,000 extra because we think it's going to be extra work. So they're either just frankly not allowed, or they're the cost kind of covers it, right? That is very important. That it's out of alignment with NERC's recommendations for modeling. You can click them there, but NERC recommends the use of equipment-specific models for reliability purposes and the interconnection process. And FERC Order 2023 is in alignment with that as well. Many or most all manufacturers of inverter-based resource equipment don't recommend the use of generic standard library models to do site-specific or reliability studies. They just don't have the accuracy or detail or fidelity necessary to actually represent a specific type of technology. If I'm doing research or long-term planning, or if there's a machine far from my study area, or the manufacturer's gone out of business, standard library models and generic models are fine for those types of things because there's no other choice. Developers themselves who are going through these processes, managing these processes, often don't want to use equipment-specific models for a number of reasons, mostly all boiling down to they want to get it to the process as fast as possible. Equipment-specific models can be harder to work with. They can cause the interconnection engineers to have extra work. They also are very accurate, and they may show real-world problems that you might not want to fix before you interconnect, because it could be a long, timely fix that could reduce revenue long term for that facility. So kind of hitting at all levels there is that generally in North America, the right models for the right study aren't being used, just generally speaking. Why is that important? And why is it such a big deal? Using the words generic and equipment-specific model kind of helps paint the picture. But here's a little thought example or thought experiment here to kind of show how it breaks down. And I'll step through here. So suppose you're given a task, and the task is to paint a car or a vehicle, right? Any vehicle. And this is kind of mapped to, show me a representation of an inverter-based resource plant. Any inverter-based resource plant, that's the task. So to do this task and the rest of the other two tasks here, if we say standard library models, the generic standard library models are those, simplified components made to, be flexible, represent a lot of different things. You have this kind of simplified paint palette, right? So it's got a few colors. The brushes, can handle it. There's not a lot of mixing or anything. You have a few separate blocks. You know what they do, and you can put them together to make a simplified picture. The equipment-specific model on the right is, imagine a full paint palette. You have the full paint palette. You have the ability to mix and match colors, different pieces, different brushes, different line types, all that type of thing. So this first task, right? If we just want to make a vehicle, show me an IBR plant, and that's this car on the left. You can see you could make that car with either a standard library model or an equipment-specific model, right? This is a simple car, simple lines, easy colors. You do not necessarily need the equipment-specific model to represent this thing, and you can do that very easily with a standard library model, right? This kind of same logic also applies. The standard library generic model here logic also applies to synchronous machines since they're standardized. The standardization leaves you with this simple picture. So same way that for this representing one IBR plant in general, a generic is fine. Representing synchronous machines in general, a generic is fine. So if we want to move on to something more specific, right? So paint me a picture of a van, right? This is a little bit more specific than any vehicle. It's a van. Same tools, same discussion as before. A little bit more detail drawn. So if I'm saying just paint me a picture of a van, you probably can get a pretty rough approximation of a van with the standard library palette, right? You could get pretty close to making this picture with your simplified palette, but you can get a lot more specific with this picture here if I have an equipment specific model. And this is where a little bit breaks down. So in the generic standard library world, the generator, the electrical, and the power plant controller models are the same, or relatively the same, for wind, solar, and BESS, with small nuance. So painting any type of specific car, you get that with those blocks. Equipment specific models with the full code and things like that, obviously much more flexibility for making a specific car, or van here. So the last experiment, or the last thought experiment here, is really specific, right? I want a Mercedes sedan, right? So this is an IBR plant, specific type, a specific manufacturer, right? So imagine like I'm building a one plant, I picked out the manufacturer, I know what I want to represent, and you have this really specific picture. And this you can make with this detailed paint palette, right? The equipment specific model, I have all the pieces of code, I have all the parameters, I have all the different shades and the lines and the brushes to make a Mercedes. Mercedes gave me the palette and the brushes, right? I'm going to have a lot of difficulty making or accurately representing a Mercedes sedan in this level of detail with a generic or standard library model. So it's kind of a simple and silly thought experiment here, but I think it helps explain a bit of why those two models are necessary and why they're different, and where they kind of break down and where they can be useful. So a real world case study here, this was done by Vestas. They actually got permission from transmission planners and those folks running those transmission planning studies to take a look at their models, right? They pulled the models from those planning cases, the ones used for regulatory compliance and things like that. They pulled those models from different facilities, and they also went to those facilities and downloaded the parameters, code, and software firmware updates from each of their facilities, and dug into the rest of the parameters there. Through this case study, you'll see the breakdown on the left here. So I'll quickly go through them here, but I think there was about 20 plants studied. And if you look, not a single one of those plants had matching balance of plant data. And balance of plant data is those cables, transformers, capacitor sizes, transformer taps, things like that. Not a single one of those 20 or so plants had matching values. For simple things like voltage and frequency deadbands, pretty much bottom of the barrel, simple model control parameters. You see the blue there, the matching is very small, about 10 to 20% at best. Very small there. So there's massive disconnect there between what's installed and what's been recorded and what's actually being used in the planning studies. Similarly, for voltage slope and voltage or frequency slope, a little bit more complex, still very simple, about similar mismatch, which means it's not great mismatch. And then protection settings to finish off with, not a single one was able to match. And this one's a little bit nuanced, and the reason for that is that some IBRs have a curve, like an infinite curve of protection, and you just cannot represent that in a standard library model. Standard library models only can do discrete protection steps. The key thing, and as we go to the picture on the right here, the key thing is that the models in these graphs and used in this study, they are all NERC validated models, right? So all of these are mod 26, NERC mod 26 and NERC mod 27 compliant, which means in the current paradigm, like we talked before, these are perfect models. They pass all the tests, they pass the regulatory requirements. But if we look at it for a second and do something a little bit more detailed, like compare that model response to something a little bit more stringent, like a fault or a voltage ride through, you get massive differences. And if we just look briefly here, the top is showing that the profile played in for voltage at the point of interconnection is the same. And if you look at the response, this is in per unit. I'm sorry, no, it's not. It's in megawatts, but you'll see that for this high voltage ride through, the standard library model actually went all the way down to zero, basically tripped, and came back online about 30 seconds later, where the actual plant and the manufacturer model and code remained online. and continue producing power, which is obviously a very different response. That's a massive response. That's a basically entire plant variance in response between the standard library model and the manufacturer model with real parameters. And you'll see a similar kind of difference in shape and magnitude also for the reactive power response on the bottom there. So it's just a simple case study with a detailed plant comparison to show that even those currently regulatory compliant models, so you're not going to get a fine for any of this, is perfectly within the process. You can see massive, similar to this, discrepancies in performance. And how do you plan for a reliable system if you can't be sure if your IBR is going to give you 80 megawatts or zero for 30 seconds? It's very hard to get useful things out of a study work when those inputs can cause such differences. So why is it modeling in detail is super important? The power system is evolving rapidly. Current stability margins are being reduced. The lights are on right now because we have stability margin, right? The lights are on because that previous paradigm with all the engineering folks and the propensity to slightly overbuild with the current technology gave us this massive pool of stability margin that we are eating into every day. Every time we interconnect something, we're eating into that margin. We don't really know how much is left, and we don't know how to continue to keep cost effective while staying within that margin. Transmission enhancements are on a much slower timescale than inverter-based resource connections. So in that timescale, you should be kind of using more IBR technologies, capabilities, control codes, advanced capabilities to more efficiently use the current power system, and also to maintain some of that stability margin. And that could be, discretely modeling everything that's there right now from an inverter-based resource, utilizing new software, new advanced controls. Say a wind farm gets a software update and they can do something to help grid stability. There should be processes to enable that and to actually do the studies to enable those things. And lastly, relying on the standard library models like we do currently, all it does is ensure that it's always wrong, one way or the other. The models themselves were made not to be exactly right for any technology, right? So we know that they're wrong. I heard a lot of people in the industry say, well, they're wrong, but they're conservative, right? And conservative in the power system world is fine, right? We want to, err on the side of not having something bad happen. But wrong is neither conservative or optimistic in the modeling world, right? You can get both false positives and false negatives, right? You could have a wrong performance could be good in some scenarios or bad in others. So we can't be sure if it's conservative or not. The best thing to do is just to make sure we're modeling something accurately and correctly. The best way to do that is modeling in detail with manufacturer specific models and actual technology. So what's being underutilized right now, and this kind of part of those links to the Iberian blackout, but these are things being underutilized right now in the US specifically. So reactive power and primary frequency response capability, both underutilized due to generic models and federal regulatory impediments. Reactive power is FERC Order 827. Primary frequency response is 842, I think, FERC Order 842. Reactive power, the reason why that's limited is that there's language in that FERC order that says you can't, you have to stay within a certain range. I think that should be fixed. Someone should file that with FERC and fix that. For primary frequency response, underutilized because it had a cutoff date. So there are numerous facilities out in operation that can do primary frequency response, but aren't included in those that must do it under that. So limitation there. So advanced frequency controls, advanced voltage controls, and weak grid support features. There's not much to impede those from the regulatory space, but you can't do them in generic models, right? I can't use a standard library generic model to represent an advanced control for manufacturer X. It's just not what they're meant for and how they're supposed to be used. This is the example of that FERC Order 827 and links directly to the IBR, or the Iberian blackout. And this is just a kind of an example of what could be left on the table here. So FERC Order 827 says within the range of 9.5 leading and lagging power factor, unless the provider has a specific range. that last piece is very important. I'll talk about that on the last slide. But um, what that means is that if you read FERC Order 827 and do nothing else different, if the transmission provider hasn't thought about it and done something extra, you've got that um, kind of orangey yellow triangle, right? That's called triangle shaped power factor limited control, which means if you compare that to the blue outline of what a normal reactive power capability would be for a solar PV, for this example, the red shaded area is all unutilized reactive power, which is a lot of that reactive power. Um, the data from the alert says about a little over a quarter of those facilities um, in the US who reported data at Solar PV and BESS for this alert specifically, over a third are operating just like this. So there are a third who are operating in a control mode very similar to what led to the Iberian blackout, or one of the causes to Iberian blackout. So all of that leads me to conclude here with modeling is hard. Data and evidence shows that the current paradigm is insufficient. We need to make regulatory enhancements to close these gaps and enhance North American modeling practices. Probably didn't need to capitalize modeling practices, but it's important. We'll name it a term here, and enhance those things, right? So just to recap a little bit, major events comprised of unexpected IBR tripping show that the current modeling paradigm is insufficient. None of them events were predicted. None of the models, even after the fact, with hindsight, were able to match. Pretty much everything I talked about and complained about today has solutions internationally, solutions in the technology space, solutions in the regulatory space. The problems we have aren't new. We have the opportunity to learn from others. We just haven't done it quite yet. There's a strong best practice available for modeling in North America. The technical debate on what a model should do, how accurate it could be, how to study those things, there's pretty strong best practice. But that best practice is often at odds with the current regulatory process. Right? You often can't do best practice within the current regulatory process. We need to enhance those processes to actually allow the stakeholders to do the best practice if they want to. Best would be to make them do the best practice. And the stakeholder-driven processes themselves, the processes for making changes and enhancements to avoid things like gaming, lobbying, misinformed votes, misinformed language, that type of thing, those processes need enhancement. And I made a little meme here with the Spider-Mans on the right, and the process, the last piece here is where we're left right now is in the US is, the FERC is the regulator. The FERC tells the NERC to do things. The NERC does that through work with their ERO members and transition owners. So theoretically, within the current paradigm, ERO members, the ISOs, the commission planners, planning coordinators, they can, under FAC 1 and FAC 2, which are NERC standards, fix all these problems on their own, right? They could, there could be an ISO who just says, I'm going to make a brand new modeling criteria and finish it, right? And just say, you must do all these best practices. The problem is, and this is why everyone's pointing to each other, and those are the stakeholders, I guess, but if I'm an ISO, I probably have a stakeholder-driven process, or my tariff is a stakeholder-driven process. And a lot of the time, if I, as the ISO, want to make an enhancement, the stakeholders say, why are you making an enhancement when NERC hasn't said anything, right? Why are you going above and beyond? It's going to cost more money, the rates are going to go up, but NERC hasn't said anything. But NERC is saying, we're not going to say anything because we trust the ERO members to do it, right? So there's a disconnect. They're pointing at each other. They each think the other is doing their scope, and it's hard to kind of process that. So what we really need is kind of all three major parties to coordinate and collaborate to make sure that there's no gaps like we see in the current process. So with all of that, just want to finish off by saying it's very hard. These aren't insurmountable problems. We need to just leverage international experience while also enabling the current processes and practices and regulatory frameworks in the US and North America to enable best practice. So that was a lot of words from myself, and I think that's it. So thank you, and we'll talk again at the Q&A.
Thank you very much, Alex, and good afternoon or good morning or good evening, everyone, depending where you are. My name is Carlo Brancucci. I'm here with Wallace Kenyon. We're both from Anchor, and we're very much looking forward to contribute and participate in this seminar. First of all, I want to thank ESIG and Breakthrough Energy for the opportunity to join you all today. I'm going to, I'll give you a little bit more of an overview of what we plan to cover during our session today. But first, many of you probably have not heard of Anchor before, so I want to give you a quick overview of the company. Both Wallace and I work here at Anchor. We are a software company that helps utilities and asset owners and developers plan for a reliable, affordable, and cleaner power system. And we do this with an integrated planning solution, an integrated planning software that is unique in its way of being able to integrate both economic and reliability planning across electric generation, transmission, and distribution. And we've heard a lot, especially yesterday from Nick, about the importance to being able to consider reliability and stability of the power system when planning the system, and also when looking at the economics of the system. And the reason we want to do that is we want to make sure that the least cost plans that we develop as resource planners, for example, lead to a system that can operate reliably or within the reliability standards that we expect from our power systems. We are based in the US and Germany, and actually Wallace and I are currently calling in from our office in Denver, Colorado. So next. So yesterday we learned from Nick and Sam about the importance of including stability as an integral part of planning, as Nick says, not as an afterthought, as well as we all learned about the fundamentals of power system dynamics, particularly looking at voltage and frequency stability. So important consideration when ensuring that the system operates reliably across all time frames. Today, we just heard from Alex how wind, solar, and batteries, in general, inverter-based resources, reshape operational reliability, and also ways how we can model and plan power systems with large penetration with these technologies, as well as many of the challenges of being able to plan for these different and novel, not so novel anymore, technologies that we are integrating more and more every day. Now, Wallace and I, instead, for the rest of the seminar, we are going to highlight the needs, but also the opportunities and the value of linking economic and reliability planning, and also highlighting how we can actually test that our economic solutions are operationally stable. In other words, what we want to do is tell you a story of how a resource planner or a transmission planner may coordinate and integrate their plan to make sure that they can truly quantify the trade-offs between economic and reliability objectives and metrics. And to do that, we are going to speak from different perspectives. So I'm going to take the role of the resource planner, or in many places also called the generation planner or the system planner. And I'm primarily interested in economics, in building the least cost system of the future. I think about every hour of the year. I think about 8,760 hours. I care about the ability to build a system that can operate and can meet demand during every hour of the year. And I'm primarily concerned about energy and active power. Well, Wallace, who is going to speak from the voice of a transmission planner, or in many utilities and system operators also called a planning engineer, he's really concerned about the reliability of the system. He thinks a lot about the system from a snapshot perspective. He's not used to think about the system thinking about every hour and every potential operating condition, but more specific, stressful conditions of the system. And he wants to make sure the system can reliably operate during those times. And he's always thinking about voltage and frequency, and about a lot of the considerations that we heard, particularly yesterday from Sam. We are going to assume that Wallace and I work at the same utility or system operator, and as you can see here from the arrows, we know each other, we have collaborated somehow, but somehow our plans are siloed from each other, and we'll tell you more later about it. And but we do see an opportunity to work more together, and we believe that is what we need to do to be able to plan for a better system, especially given the great change that is going on that we've heard yesterday and earlier today from Alex. So let me start telling you a little bit about my job as a resource planner at UtilityX. My objective is to plan for generation and storage development to ensure adequate, reliable, and least cost electricity supply. So my job is really to plan what is the optimal mix of resource assets of generation and storage that I need over the next 10 to 20 years to meet the needs of the system, so demand of the system, but also to meet any other goals that my company may have or that may be dictated by regulation. The way I think about planning is generally I'm going to think on a multi-year framework. So I'm not going to plan for 1 year, I'm going to plan for the next 10, 15, 20 years. And as I said earlier, I really care about the operation of the system during every hour of the year. So I'm always going to be looking at 8,760 hours of the year. I'm also going to consider uncertainties. So I'm planning for the next 10 to 20 years, but I need to develop plans that are adequate for a wide range of potential futures. And uncertainties include projections for demand growth, projections for technology and fuel costs and how those may change over time, as well as, more and more importantly, weather variability, as this not only impacts the way we consume electricity, but clearly has a major impact on our renewable resources like wind and solar. To do my job, to develop these generation plans, I primarily use 3 types of modeling tools. Capacity expansion models, those are going to be optimization models that optimize investment strategy. So in what type of assets should I invest and when, and maybe where, meaning I may have in my capacity expansion model some level of geographic representation and some level of transmission representation or transmission constraints between different regions or zones, or maybe even nodes in my system. I'm going to use probabilistic resource adequacy assessments, where I'm going to run probabilistic models to evaluate the ability of the system to meet demand during every hour of the year under different potential futures. So looking at different potential weather years, different outage conditions of my different assets, etc. And finally, I'm going to be running production cost models or optimal unit commitment economic dispatch models to evaluate how the system will operate on an hourly or sub-hourly basis under different future generation mixes that I may be evaluating, or different expansion plans that I may be evaluating to ensure the system can meet demand and ancillary service requirements every hour of the year. Things I'm going to be thinking about are definitely resource availability. Do I have available fuel? Do I have available wind and solar resources? In some cases, I may consider transmission constraints. And the reason I highlight in some cases is because depending where I am and depending on the condition of the system, I may not consider transmission, or in other cases I may, and that is a function of the reality I'm planning for, as well as maybe the level of sophistication of the modeling processes I use. And then I'm also going to be thinking about ancillary service provisions. Something very important. So as I said, I'm playing the role of the generation planner, but I do interact with a transmission planner or a reliability planner. And how do I think about this person? For me, Wallace is the person that actually defines transmission and stability constraints that I do consider in my models. And depending, I'm going to consider them mostly in my production cost models, but I may also consider them in my resource adequacy and capacity expansion models. So I'm talking about considerations such as MONCON or monitor contingency pairs, so security constraints. So I want to make sure that when I model the optimal operation of the system, I'm doing it in a way that is secure against potential contingencies in the system. I want to consider ancillary service requirements, primarily in terms of frequency regulation, so regulation reserves, load following reserves, and other type of inertia and frequency regulation reserves, but also potentially other ancillary services requirements that the transmission planner may be able to provide, such as voltage regulation reserve. Must run units, so generation units that must be online, or minimum generation levels that I need in a specific part of the system, either any generation or specifically minimum synchronous generation in the system or a specific region to ensure that the system can operate reliably. And I trust that Wallace, the transmission planner, can provide me those constraints in a way that I'm going to be able to plan the generation of my system and ensuring that it operates reliably. That's his job, and I'm going to trust that. The challenge is most times he shares those constraints as one constraint for the entire area. So I'm treating stability or transmission constraint that he derived probably from a single snapshot, and I'm applying it across the entire area. And we're going to touch more about that, but this is something I do want to highlight. And so I'm going to pass now the word to Wallace, who will walk you through his job as a transmission planner and what he does on a daily basis.
Yeah, thank you very much, Carlo. It's good to hear about what you do over there on the other side of the office cubicle, your generation planning activities. So my role as the transmission planner, it's a variety of different elements in the minutia of what we're up to in the transmission planning domain. But writ large, my primary objective is to ensure the reliability and stability of the high voltage mesh interconnected bulk power system. And I'm going to do this through a handful of both current and future infrastructure assessments. How do we do this? How do we think about this? Well, a lot of conversation has already been revolving around this idea of snapshots. A lot of the modeling efforts that I employ as a transmission planner are very detailed, very computationally intensive. And as a result, it's generally not pragmatic to think about going to every operational hour of a year, 8,760 for a single year. And when we think about different types of scenarios, it really blows up in complexity and magnitude. So we pick these snapshots that are intended to sort of encapsulate what we expect to be the most stressed periods of the system operation will be based on the fleet and the loading of the system under those conditions. So we'll take a handful of snapshots. They might be representing nearer term operational scenarios, or perhaps future 5-10 years out based on the sort of resource development plans that the generation planners have come up with. And we'll use those to then apply a variety of different types of modeling efforts. Generally, we're looking at sort of coincident loading generally across our bulk system. A lot of that has to do with sort of the changes in the way that system is loaded. We can look at more real-time data to get ideas of how operational profiles might be changing, and then use that to cast forward to look at how the system might operate in the future. But generally, looking at peak and shoulder as two primary at-risk operational periods, and then, based on what we find with our analysis, we might bring other periods into the objectives of what we'll be looking at. So what are the types of modeling tools? Yesterday we heard a lot about voltage and frequency stability, and a lot of discussion about what has gone wrong in particular systems around the world. Today, Alex was describing a lot of the challenges with IBRs, but how do we actually make decisions based on all these different criteria and the conditions and the types of responses of those assets? Now, in the modeling tool domain, we could really kind of bin them up into three broad categories. And I would say the first one is really the most basic and probably the simplest from a computational perspective. And that's really just basic power flow assessments. So we'll be looking at steady state and transfer capability. When we're talking about steady state, we're looking at the AC power flow loading of our system based on the operation of all of the generation assets and the demand on our system. We'll use this to do steady state contingency analysis, whether single component loss, cascading component loss, where you'll be looking at the follow-on effects of loading based on initial losses, or you might be looking at sequential contingencies, where you're considering first perhaps the loss of a generation asset, and then later on you want to look at a tranche of high voltage lines and see what happens if there's a near coincident loss of those assets. Those help us uncover the potential for sort of cascading failures in our system, which is what we see in that image on the bottom there. The other type is transfer capability. Now, this is where we'll be looking at, really getting into sort of the voltage stability aspects from a loadability perspective. And that's understanding how close to an instability point, which Sam talked about at length yesterday, you might arrive at based on the loading of your system. Next up, we get to the analytic stability, where we're not in the time domain space just yet. Although what you'll do is you'll notice that there is a time domain response for short circuit. So the image that just popped up on the bottom is showing the faulted response of a synchronous generator and also an inverter. This is actually an element of change in contemporary systems with more inverters, is that where in historical systems you could use analytic approaches only to find what your short circuits were based on a synchronous generator response. The digital control of IBRs implies that there is an element of time domain analysis to find those short circuit responses. So we could argue that those live both in the analytic and also the time domain as well. But in the top, we have a classic eigenvalue trajectory analysis. Now, what we're doing here, it's also referred to small signal stability, is we're trying to understand if the controllers and the assets on our system are going to be stable if I dispatch them in a particular way. So this allows me to look at all of the controllers and, without the presence of a contingency, understand if that system is stable in that particular operating condition. Finally, we have our time domain assessments. We heard a little bit of discussion about phasor and waveform, also known as EMT domain, earlier from Alex. Those are going to be what you would consider the most rigorous type of assessments modeling tool domain. At the top chart on the right there, we see a frequency response where we're looking at both measurement data as well as a phasor and also an EMT simulation output. In this case, we're looking at frequency stability elements in that chart on the top right there. So looking at how the system responds usually to, say, a loss of a larger generator. And then down at the bottom, we're in the waveform domain. We're actually looking at the fault response on just, it looks like a 4 cycle fault of our system where we're comparing measurement and PSCAT data. So those are the sorts of modeling tools that we're using to do these assessments. Now, with these modeling tools and with the scenarios and the objective come a variety of challenges. Mostly building and handling these high fidelity models can be quite cumbersome, and that sort of gives insight into why particular snapshots were chosen in the first place. Because to have enough detail and enough data to actually run meaningful models that are validated is a very, very challenging task and requires a lot of inspection and checking and validation. Another challenge is really just developing and conditioning these representative cases. Remember, we have to build a case that represents the system's exposure to risk and understand if that allows us to make a decision based on the operation of the system. Finally, how do I think about resource planning? How does a transmission planner, perhaps in general? Well, we consider they're configuring the economic operation of generation resources. I say minimal physical considerations only based on the sort of challenges that exist in the transmission planning domain. It's not practical to bring all of the controller gains and filter components and filter characterizations into economic tools. We have to simplify things to get computational tractability. So what the objective of my job is to figure out which constraints are reasonable and meaningful to economic planning to bring them back in. And again, what Carlo was emphasizing previously is that generally speaking, what they'll do is take the results of snapshot analysis, derive constraints, and then apply them to many and/or all hours of the year. So that's the overview of transmission planning, a lot going on. How would that look in traditional power systems? So, before, back not so long ago when a lot of the material that Alex presented discussing sort of the challenges and the nuance that come with IBRs, historically we were operating our systems with very large centralized generation. We would have generally unidirectional power flow, not across the transmission necessarily, but really from generation to what would be considered passive customers on our system. So generally speaking, transmission planners would supply a set of initial constraints to resource planners to understand how they might populate the constraints in their capacity expansion models and production cost models to then see how the system would run based on a variety of scenarios in the future. And then transmission planners would go in and apply due diligence to understand the stability of the system across the range of these different scenarios. Now, what's actually changing out of these sort of like this unidirectional siloed planning process that worked really well is that in modern power systems, there is a whole lot of different and interesting and new things going on. So we're having multi-directional power flow, particularly on distribution systems where you have many, many more assets who are responding to different types of signals. You might have distributed energy resources that are trying to play in the market to a certain extent. You have solar on rooftops that are coming online when the availability is there, the resource availability is present. And then of course not being online when it's not available, which sounds innocuous, but really from a transmission planning perspective, understanding the resource availability and where the power is coming from in these snapshots that I'm looking at is very, very important and challenging. And it brings in a very large variety of operation of the system. So we have decentralized and variable generation as well. So rather than having very large centralized generation that are, to Alex's points earlier, large thermal assets with rotating masses that are easily characterized with a relatively smaller set of parameters, now we have a multiplicity of power electronics based resources, IBRs, if you will, which can be, digitally configured to respond in a host of different ways, and there'll be many, many more of them across our system. So what this really side of indicates is that when Carlo is sitting over here doing his generation planning activities, and I'm over here doing my transmission planning activities, what's starting to happen is that the cost of these silos is becoming quite significant. We're having, unforeseen reliability risks that are coming up in our systems. And why we're not seeing them is it's really to a variety of different points. Maybe we're just not accustomed to looking at particular times that are in fact at-risk periods, or we just, aren't really adopting our methods to look at our systems in new ways. Now, these transmission constraints, of course, have a significant impact on the economics of renewable generation and storage deployments. If I can't appropriately characterize any sort of constraints on the system, then the economics of that particular asset might be null and/or it may not be a very good choice at all. So this really indicates that as the grid is transforming, we really need to start thinking about integrated planning, which is really bringing together our generation and transmission planning activities, the economics and reliability, if you will, and tighten up those feedback loops so that we can more appropriately arrive at an appropriately designed system. Now, just to sort of recap sort of what we've been talking about for the last 2 days at this point. In modern power systems, there's a variety of different challenges from the transmission planning perspective. Now, there are, of course, changing technology types. Inverter-based resources are coming. They are achieving not just much larger annual energy participations in systems across the world. As a result, they're also achieving much higher instantaneous power contributions. Now, those two things, Carlo was talking about how he thinks about energy. That's very much in the resource planning domain. But as a transmission planner, the instantaneous power is really what I'm thinking about from a snapshot perspective. So it's an indicator that we need to be thinking about our snapshots and perhaps in a different way. There is, of course, an increased quantity of these generation sources. We have more smaller assets. And, you know, kind of one of the topics of the yesterday and today is that there are different system needs that require attention that traditionally we weren't necessarily paying attention to. Now, what I mean by that is there's this idea of voltage forming. IVRs as grid following assets works really well at low penetrations, works really well with historic paradigms. But as we start to put more and more of them on the system, suddenly we have to be thinking about who's actually forming the voltage profiles. That was something we always just got because of synchronous generator basic characteristics of rotating machines. But now it's a thing that we just need to think about from a planning perspective. Similar, not necessarily the same, there's this idea of inertia. Inertia is, of course, a way to gloss over transients until a governor can actually take action in a synchronous generator. Over the last 100 years, we've designed systems to rely on it. Now we have to think about how we operate systems with lower levels of what I would call physical inertia, because inertia as resistance to change is something that IVRs can very easily provide. Accurate and effective models, that's always been a problem. But with the growing complexity of IVRs, the proprietary nature of IVRs, and the multiplicity, it becomes much harder to get all of the data needed to do all of the different types of modeling activities. Device configurations, Alex was discussing digital control of IVRs, whereas historic systems with synchronous generation, you would get the response you got because of the physics of the device. Now we have to think about how we're configuring how IVRs will actually respond, because everything is designed based on what the engineer is interested in. It's digital control. It's with great control comes great responsibility, you might say. Finally, there's this idea of adapting existing workforce tools. We're not just going to come up with brand new tools immediately. We have to think about how we can coordinate these tools in more effective ways and also use the existing ones to meet current needs. Here I'm kind of indicating more at the phaser EMT domain. There's a lot of dialogue about the inadequacies of phaser domain tools and the need for EMT, but we're going to have to think about how we work with them together and understand when each is applicable. And then finally, there's, you know, I wrote compliance at the end. I haven't thought about whether or not to have this in here, because compliance has always been a challenge, right? You have to get, you know, if you have assets that are saying they're going to do something, if they don't, then your system might fall apart. But it just becomes even more of a challenge considering the growth and quantity of devices on the system. With that, I'm going to send it back to my colleague, Carlo, to tell you about modern power systems and challenges from a resource planning perspective.
Thank you, Wallace. And yeah, I'd like to share with you now some of the, you know, Wallace highlighted a lot of the changes happening and how, in the power system, and how that's challenging his job as a transmission planner. From a resource planner perspective, one of the things I need to consider is how the variability and uncertainty of generation sources, primarily wind and solar, affect the way I plan for generation, storage, and operational strategies of my system. Another thing is, unless I plan a system that is used to a lot of hydropower and pumped hydro storage, I wasn't used to operating storage much in the past. And so now I need to learn how to plan for an asset that sometimes acts as a generator and other times acts as a demand, and most importantly, whose operation depends on how it was operated in previous time steps. So storage can only generate if the state of charge is higher than a minimum threshold, and that's dependent on the ability of the system to store energy in the assets in previous periods of time. As was mentioned, I'm now dealing with distributed generation sources, meaning that now all the generation is not connected to the transmission system, but I actually have to deal with the fact that my demand may be significantly more variable, and in some cases it may act as a generation source, or I need to plan for utility scale generation and storage sources, considering that during many times of the day or of the year, a lot of the demand will be met by distributed resources connected to the distribution network. Then I need to also plan for potential new sources of demand flexibility. There is a lot of new demand of electricity that can provide response and flexibility, and this is being highlighted recently also with the interconnection of much larger demands that are going to have a major impact on the system, but at the same time could be a flexibility resource for the system given their magnitude. And then finally, I have to deal with uncertain and changing policy and regulatory conditions. A lot of my plans are economic driven and incentive driven or policy driven, and those incentives and policies will change over time. So how do I take that into consideration as I plan the future resources of my system? So the question now is, we heard about what I do as a resource planner, what Wallace does as a transmission planner. We discussed the challenges of modern power systems in the way we plan for the economics and for reliability of the system, or for generation and storage assets and for transmission assets and upgrades. And we talked about the need to integrate and coordinate our planning processes and the cost of not doing so. So how do we do that? So as you know, the community has been talking for a while now about the need to integrate planning processes across generation, transmission, but also with distribution and customer programs. And this is one example of the many diagrams that exist that show the integrated workflows that could be established to better integrate and coordinate planning processes across different planning domains. What we are going to be talking about for the rest of today's presentation is we want to unpack the arrows that we see here between generation economic-driven studies or planning processes with transmission/reliability-driven planning studies. So to do that, we want to highlight a framework on how Wallace and I can work together, and how can we integrate our modeling efforts and our planning efforts to ultimately arrive to a better integrated generation and planning solution that quantifies the economic and reliability trade-offs of our plans. And this is something we've been thinking a lot here at ENCORE, because we're a software company that develops SAINT, which is an integrated planning solution that indeed enables the workflow that we are going to be highlighting today. And we do believe in the power and the need to be able to do this in an integrated framework in a way that allows Wallace, that is used to use a set of modeling tools, and me, that I'm used to use another set of modeling tools, allows us to collaborate in one platform with a common data structure and database, common view of the system, and consistent view of the system in a way that is seamless, and in a way that it encourages collaboration between us rather than creating barrier of collaboration. So the first thing is, we're going to start with a planning case, where we're going to be defining a case of the future for which we are planning for. Second, I'm going to be in charge of running my resource plan, so planning for the economics of the system, primarily running production cost models driven by the outputs of both capacity expansion and production cost models. And then I'm going to be sending information to Wallace, who's gonna be in charge of evaluating the reliability of the system during different conditions. We're gonna walk through each of these steps in much more detail. That's why I'm going much faster right now here. And afterwards, Wallace what's gonna do is going to let me know if the power system I've configured in the future can actually operate reliably. If not, he's gonna provide me two types of feedback. One, he may define some necessary transmission upgrades that may be required to ensure that the system can operate reliably, or two, or he may define some operational constraints. So he's gonna define constraints on how to consider or model transmission and or allow generation to dispatch to ensure that the system leads to dispatch conditions that lead to a reliable operation of the system. And then we're going to iterate here to compare different potential plans that we have for the system, both in terms of different expansions of the system, but also comparing the impacts of different potential operational constraints and upgrades that may be that could potentially resolve the same reliability issue. As a simple example, do I upgrade my transmission system by building a new transmission line, or do I set and operate a dispatch constraint that lead to the same reliability outcome? What is better and how do I compare them? This framework allows us to compare that. So let's zoom in quickly into the first two steps of this integrated framework, and let's talk about defining the planning case and defining the optimal system expansion, primarily in terms of generation and broader resources, so storage in the system. I've already talked a lot about this earlier, so the first thing is I'm going to do is I'm going to run a capacity expansion model to give me the optimal expansion of the system in terms of primarily generation of storage sources. Then I'm going to run a resource adequacy assessment to evaluate loss of load expectation or the ability of the system to meet demand during a wider range of potential operating conditions, considering different weather areas and considering different potential generation outage conditions. Then I'm going to disaggregate this into a production cost model to evaluate the operation of the system for every hour and potentially for sub-hourly time steps throughout every year that I am planning for. The bottom left graph here highlights the potential way of representing transmission in any of these models. I could have a zonal representation and I could have a nodal representation. There was a question in Slido that came a few minutes ago that is an excellent question for me to address now, which is integrated resource planning should include generation, transmission, and end use, including demand side management. I'm not sure if the discussion here are really addressing IRP. That's an excellent question. In resource plans, we are going to find in different parts of the world, transmission is not considered at all for a wide range of good and bad reasons, depending on the region. But regardless, even if I have the information, the data, the knowledge, the tools to model, to run resource planning models that have full detailed transmission representation. In other words, if I could run nodal capacity expansions, resource adequacy, production cost models, there is still a lot of detail from a transmission perspective and from a reliability perspective that I am not capturing, because I do still have to simplify the way I represent transmission in my system. And I'm not going to get into the details, but a couple of things I want to highlight is that I'm not considering voltage, I'm not considering reactive power flows, and I am only considering the impact of contingencies up to a certain extent. So regardless if I'm running a resource planning model that has detailed transmission representation, everything we've told about the need to iterate between resource and transmission planning still stands, and the value I gain from working together with Wallace still applies, because he's going to be able to provide me reliability considerations and constraints that I cannot capture in my resource planning models without him running the more detailed stability studies that he does to plan for transmission and for the reliability of the system. So once I'm done with my production cost models here, I have set realistic operating conditions. So hourly dispatches for every generator of storage and demand in my system, for every hour of the year, for any of the scenarios I'm evaluating for the next 10 to 20 years. And that's what I send to Wallace, and that's where he's going to now walk you through how he completes the feedback loop in this integrated workflow.
Yeah, thanks, Carlos. So, you know, he's talking about sending out the whole 8760 hours of the results of his resource plan, which is a cumbersome thing at best from a transmission planning perspective, where I'm mostly thinking about snapshots. But one of these initial efforts with mapping and bringing what we consider to be the active power dispatches of all of these different devices, and then sending them to their, or really just keeping them and representing them within their generation asset configurations within their these transmission planning tools like an AC power flow steady state tool, is that it allows me to look at the operation of those different assets across the system to better understand when there might be at-risk periods based on screening activities. Now, you know, keeping an eye on, you know, these planning activities take a long time, and sometimes you run out of time, like today. But really what we're doing is we're taking from the resource planning, we're really looking at the active power commitment based on these particular operations of these scenarios in future cases, as well as what they might be providing from an ancillary service provision. And, you know, to some people who are looking at this, they might be thinking that this is, well, this is very similar to what they do in operations. And I think that that is a common refrain in the integrated planning spaces, that we could think about that as bringing operational behaviors a bit closer into our planning activities. And really, it's to better understand the potential response of a system to these future conditions. So what I've done is I have got my active power set points, I have device status, and in this case, I'm really talking about commitment. Commitment plays out very, very heavily for all of the different reliability things that we'll be looking at, from steady state all the way to the most granular type of analysis. And then finally, understanding who's providing what and when allows me to better understand the response of the system to contingencies. Now, in this initial portion of the workflow, there's this idea of conditioning. Now, again, historically, when you're looking at snapshots, you might be conditioning your large system, Western interconnection, Eastern interconnection, based on the loading of particular assets. You know, in the 21st century, we have a lot of computational upgrades that allow us to actually run power flow tools with a much greater range of convergence. And with that in mind, it's a little bit easier to look at a broader range of hours of operation of our system to understand what sorts of conditioning insights we need to derive. In particular, you know, this chart is showing a very interesting episode of the commitment behavior of a peaking power plant that's helping you regulate voltage in a particular region of your system, which when it's turned offline, you're actually using the ability to sync reactive power for a lightly loaded transmission line, something we're familiar with based on Nick's talk yesterday. So being able to go there and understand helps us uncover some of these stressed operating conditions. But how do we select these for further analysis? Like, how do we decide which snapshots to go forth with and do the more detailed types of analyses? Well, there's a variety of different things we can think about. Peak loading, shoulder loading, those are very historic. Light load as well, when you might have very different operational characteristics. Other things we might be thinking about, you know, what sorts of criteria based on maybe IVR shares could I be looking into to help understand which periods I need to be looking at? Can I look at high instantaneous penetrations of IVRs across the entire system? Maybe in particular regions where I might have what's you know, generally considered a weak system and may have poor voltage regulation capabilities. If I'm looking at large you know, transfers between regions where I might have some susceptibility to you know, looking at a rotor angle stability as a traditional type of stability analysis. Those are ones I could be looking at, but it remains to be seen how, you know, based on all of this, you know, we keep talking about this very diverse type of operation of our systems based on all the different IVR behaviors, the resource availability, the consumer behavior of DERs. How do we ensure that we're capturing meaningful periods? And this is a space where sorts of machine learning type analysis of data could help us understand the loading of our systems in a more interesting and rigorous fashion, where we can actually look at the operating conditions across an entire year, or maybe a quasi-static time analysis of a week, 168 hours, to understand which times are actually susceptible to certain types of instabilities. So once we exercise our conditioning, sort of identify conditioning elements via violations and do some filtering, well, then we arrive at this point of reliability screenings. Now, the way we're going to think about this is not, we're going to think about this as tiers of lower effort to very high effort, and how you would actually use these different tranches of types of screenings to arrive at the more detailed types of analysis at the very end of your assessments. Now, again, with an eye at the computational performance in the 21st century, there's not a whole lot preventing us from doing targeted steady state contingency analysis at many, many more hours of the system than we're historically used to. So this could operate as a first pass screening, where we can be doing the sorts of n-1, -x, cascading and sequential contingency analysis. If you're doing interconnection studies, we could be using this for injection and withdrawal studies as well. And this helps us understand, whereas initially we were just looking at the loading of the system and perhaps the IBR shares, we could use our steady state contingency analyses responses to better understand what times need more reliability screenings, and where we would step farther into the types of analysis. Another type of steady state transfer capability assessments, these, tend to be very, very dependent on the commitment of assets, which is something that's fluctuating more and more in contemporary power systems. So in particular, the voltage limiting and voltage collapse that you might see based on resource availability with reactive power capabilities, again, something we were talking about yesterday, those sorts of elements we can be looking at as well, using the broader computational capabilities of tools today. We get into the analytical type tools that we were discussing before. We can use short circuit assessments to help us identify weak grids. These are stability proxies, generally speaking, for IBR shares. Another type that lets us filter down to the more which snapshots are really the ones that need to be looked at the most aggressively. Small signal stability analysis, is the dispatch of the system actually stable based on the types of controllers associated with the IBRs and the available synchronous generation that's actually present. Again, these are really more sorts of filtering to help us get to the very, very time intensive types of phasor domain analysis and also waveform domain analysis, where in phasor domain we're thinking about frequency stability, so we're really focused on perhaps IBR shares, but also more contemporarily we're interested in the broader system inertial response. So what sorts of behavior am I getting from my inverters that are helping me regulate frequency that I might have assumed was present just based on synchronous assets. Critical clearing times sort of in the rotary angle stability space, and also looking at short-term voltage stability, where we're considering the reactive power behavior of assets. Can use these to look at sorts of compliance type sensitivities from a scenario analysis perspective. And then finally, who's actually available to provide reactive power when it's needed. Something Sam was talking about yesterday. Finally, we get to waveform domain analysis, the smallest blob, but the most time intensive physics-based type analyses, where the need generally correlates with IBR shares, not always. Remember, EMT really came up with HVDC, which is not necessarily an IBR. Looking at subsynchronous oscillation analysis, harmonics, we're thinking about those two new types of stability assessments required in the IBR space. So we do our reliability screenings, and then based on which regions and which times required more analysis, what we arrive at is a set of constraints that we need to take from my transmission planning domain. I need to encapsulate these, and I need to provide them back to Carlo so that he can more efficiently encapsulate them in his economic optimizations, so that he can do the types of analysis to provide insights into the overall costs of the system, whether it's an operational constraint where I might actually just say, well, for a few hours of the year, I'm okay if I have to curtail these particular assets. That might be a cost we're willing to swallow. Whereas if it's a broader capacity expansion to actually bring certain power and certain devices to market, then that's a whole different thing that we're considering about. So really, we're taking all of the things that we uncover with transmission and encapsulating it in the various types of constraints that we've talked about previously in the generation planning space. And then finally, as we do, we have to compare and identify which solutions we would prefer to use. The data being shown here is completely just representative of the type of analysis where you'd be doing a type of cost benefit based on operational and or capital build out solutions based on the different types of assets that we're looking at. So what we've done is we've done our screenings, we've done our reliability assessments, we've figured out if the system is stable, or we've decided what the system needs, and then we've sent this back to the economic team, the generation team, and they've been able to say, well, if you're going to constrain it this way or require this build out, it's going to increase the cost of these systems by X amount, and then we can sort of get into this cost benefit trade-off analysis. Yeah, anything as a generation planner, would you add anything to what I just said there?
No, I would say that what is key is going to be to iterate, because once Wallace sends me additional constraints that are necessary to maintain reliability or additional transmission upgrade, it may lead to a suboptimal expansion with respect to what I planned before. So I may need to take that into consideration, rerun my resource planning models, send back my outputs to Wallace, and iterate until we arrive to a convergent, both economical and reliability solution. And that is only possible if we create a framework, or we have a framework available to iterate between us.
Yeah, that's a really good takeaway there. And I think what you'll notice from the flavor of the presentation is that none of these sorts of analyses are really different from what's being done, but we're just thinking about them more as a framework to promote iteration to help us get to the better trade-offs between these economic constraints and these reliability constraints, to understand really what the system needs across this great big variety of potential operating conditions. So when we have something like what happened with the Iberian Peninsula, it's not necessarily a surprise because we've gone to those spaces and understood what the operational conditions are. Of course, in that case, we would be more concerned about what's going on across the world, like amongst all of these different operational conditions of systems across all of the different continents. Like, how can we best understand when we're getting closer to these sorts of reliability issues? And these frameworks, this framework in particular, allows you to get there a lot sooner using the computational improvements present in the 21st century. So with that, I think would you add? I think we're actually pretty much at time for the webinar. So
But that's all, and thank you all again for the opportunity and for listening. And we'll pass the mic back to Alex to moderate the few minutes we have left for Q&A.
Thank you both. Yeah, we got 4 minutes left, so I think we'll just do rapid fire from the top. I'll keep my own rule, hopefully, and stick to a couple second answers for each. And I'll just go over from the top down. So someone asked what we can learn from other parts of the world. And the first thing we can learn is to look at their grid codes and see what they're doing with their grid codes. They treat things differently based on technology. They have very detailed, very specific modeling and model accuracy requirements. And the goal would be to learn from them before something bad happens, right? Most of the reform in Europe and internationally has happened after a major blackout, because usually you don't get leverage to do it until that happens. So us in North America, I think we want to make sure we can learn from what they have done after those events and implement those before we have an event like they have had. So on that one, anything to add, y'all, on that first question of what we can learn from international? Great. Second one. Oh, go ahead.
Alex,
Hank, is that you?
This is Nick. Can you hear me?
Hey, yes, I can. Go ahead.
I just we got to bleeped over my closure slide, and that's okay. But I do
Oh,
want
you're
to make
right.
one or two words. One
Yes,
or two
please.
words to wrap up the 2 days. I don't need to read these off, but I hope everybody was particularly attentive for about the last 4 slides that Wallace presented, because that's the culmination of 2 days of what's going on in this iterative process. And you should take away, the critical thing is we can make better decisions with that integration. There's a bunch of things that need to happen that are listed here. And so we are on, as an industry, a trajectory towards doing better. in this complicated space. I also want to make a cautionary point, and then I'll be quiet, and that is regarding data centers. All right, we talked about data centers. We are at the risk, everybody on this call is at the risk of being the generals that have figured out how to fight the last war. And the level of disruption that is coming with data centers, I cannot emphasize how huge it is. And a lot of it is retrograde. Those people that are on the call here that are policy people and regulatory bent and everything else, we are going backwards. And I just worked on a massive, massive data center in which the system engineering was comically inadequate. And all the good stuff that you heard in the last 4 hours of lecture was 90% ignored. Solutions consisted of, we will take a snapshot of the peak load, we're going to throw gas turbines and 40-year-old transmission line design at the problem until we get one spot in space that works. We're going to ask our regulators to approve billions, multiple billions of infrastructure based on sophomoric engineering. Really, really frustrating. So all of this good stuff that we talked about for the last 4 hours, mostly in the dumpster. And I'm very frustrated, and everybody on the call should be scared. All right, off my soapbox, back to the questions.
Thanks, Nick. We're just at time, so let me just rapid fire a couple of really specific questions, just 3 here, and then we'll be done for the day. But the ones I don't cover or we haven't covered of the other maybe 18 or so questions, we'll put those answers together and post them with the recordings. There's a question on if vendor-specific models are wrong also, in those ones in the events. We don't know. Every event except for Odessa's 1 and 2 were in the WEC, where only generic models are allowed to be used. So I believe only one of those many affected facilities used a user-defined model. That one also wasn't representative, but that could be for any of the other reasons of misuse. The second one, really quickly, has the number of events decreased? None since 2023. They haven't decreased. They're still happening. The reports aren't coming out as regularly as they were. If you look at the 2 4-year windows, the second 4-year window, 2020 through 2023, there's twice as many megawatts that tripped offline than the first window. So they're actually accelerating at a very fast rate. There's questions on, this is the last one before we close it out, but there's questions on IEEE 2800 and 1547 and 2000.2. Those help, but they don't solve anything, right? Those are voluntary standards. Those are voluntary standards with good technical consensus, but voluntary standards aren't enforceable, right? So voluntary standards are only enforceable if one of the entities makes them enforceable. So while they give us that basis of engineering consensus and technical consensus, they are not real in the sense of making someone do something until an ISO or an RTO or a NERC FERC says you must do that. So we need to make sure that those types of things are implemented into these processes to close all these gaps. So with that, in 2 minutes over, thank you both for presenting with us today and for participating. We will send out responses to the rest of the questions with the slides and with the recordings. And with that, and I don't want to reiterate what Nick said, but please remember what Nick said, that we should be scared and use that scaredness to close these gaps and to move everyone forward. So thank you very much. Thanks for participating these last 2 days, and we'll talk again. Thanks.
Thank you, everyone.
Thank you. Bye-bye.